Hi, in this video we're going to talk a little bit about domain, just as a little refresher to remember the key ideas about domain. We're going to see that a lot in calculus this semester, that we're going to need to be able to think about the domain of a function. So in general, when we think about the domain of a function, we're thinking about the values of input. So for all of these I have x for the input here, but the domain would be the values of input for which there's a valid output. Okay, inputs for which there is a valid output. So if we're talking about functions where we have real number inputs and real number outputs, we're talking about some set of real numbers here for which we get a real number output. And for our purposes in this class, there's really four main things that you need to think about with domain. So in every function that you're looking at, there's really just four main things that you need to think about with domain. One of those is that you need to make sure that you have a denominator. If there is a denominator, you want to make sure that that denominator is not going to be equal to 0. Because 1 over 0, any number over 0, 0 over 0 is undefined. That's not a real number output. So I need to make sure that denominators are not equal to 0. So you can see in these examples here, I've got a couple of functions with denominators. I would have to worry about that in those functions. Another important thing to think about with domain is that we want to make sure that if I have radicals, that the expression inside an even index radical, so a square root or a fourth root, that expression inside the radical, that's called the argument of the radical, that expression inside the radical here, that argument needs to be greater than 0 or positive. The argument of the even index radical, not greater than 0, greater than or equal to 0. We can take an even index root of 0, greater than or equal to 0. The next important thing to think about, so we've got some radicals here. The other important thing to think about is that we also have some restrictions with logarithms. So if I have a natural log of something or any kind of logarithm of something, that argument of that logarithm, that expression inside the logarithm, that expression needs to be greater than 0. So the argument of the logarithm needs to be greater than 0 or positive. One other restriction, which I don't have an example here, but we'll maybe talk about in another video, is that when you have inverse trig functions, each of the inverse trig functions has some different restrictions on its domain. I have an ordinary trig function here, so I don't really need to think about that with this one, but each of the inverse trig functions, they all have different restrictions on their domain. So there is a video that just focuses on those inverse trig functions and their restrictions in a separate video. All right, so for these functions though, thinking about the domain of these functions, we're just going to look at each of these and kind of go through this little mental checklist and make sure that we're thinking about all the things we need to think about for the domain of these functions. So for this first function, f of x, the only thing that I have here in this list, denominators, even index radicals, logarithms, and inverse trig functions, the only thing from this list that shows up in this function is this denominator. So that's really the only thing I need to think carefully about when I think about the domain of this function, is that I want that denominator, which is just x, to not be 0. All right, so that's what I'm thinking about when I think about the domain. When I write the domain of that function, though, I want to write about what x can be, the inputs for which there is a valid output. So this tells me what x cannot be. So the domain would be all real numbers except 0. If I want to write that in interval notation, I could write that as negative infinity to 0, not including 0. Use the rounded parentheses there to indicate not including 0. And then from 0 to infinity. So this is the union symbol, which means that we have the union of these two intervals. So this interval, that interval. X can be in either of those two. Both of those two things together is our domain. All right, for our next function, g of x here, I have a couple of different things to worry about here. I have a denominator that shouldn't be 0. So I want to make sure that x minus 1 is not 0, or x is not equal to 1. But I also have this restriction here with a logarithm. I have this expression inside the logarithm. And so I need to make sure that that expression inside the logarithm is greater than 0. So x plus 1 greater than 0, or if I just subtract 1 from both sides of that inequality, I get x is greater than negative 1. All right, so this is my little work here to think about the domain, but when I write my answer, I want to write that in interval notation. So I tend to think about this in terms of a number line. And so I've got x's that are greater than negative 1, except I need to exclude x equals 1. So I'm kind of visualizing a number line. And I would think about starting at negative 1, not including negative 1. So I've got the rounded parentheses going up to 1. But then I need to exclude 1. So I'll stop at 1, rounded parentheses. And then I can use values on the other side of 1. So 1 to infinity as well. So the domain is both of those two intervals. X can be in this interval, or x can be in that interval. All right, on this last one here, we have a radical. And so even index radical, so I need the argument of that radical, that expression inside that radical, to be greater than or equal to x squared minus 9. Greater than or equal to 0. Okay, so we might think about adding 9 to both sides here. So I have x squared is greater than or equal to 9. You need to be a little bit careful about what you do next, though. Just taking the square root of both sides of this doesn't quite give you the answers you need. There's a little bit of that in the very first section of material for this week, where we looked at inequalities. And looking at quadratic inequalities like this, I tend to just look at that and think about that. Think about what kinds of numbers that I can square that I will get results that are greater than or equal to 9. And remembering that when you square negative numbers, they become positive. So certainly my x's can be greater than or equal to 3, but I also can have x values that are less than or equal to negative 3. When I take negative 3 and square it, negative 3 squared is 9. That'll satisfy the equal to part. When I have values that are less than negative 3, like negative 4, and square it, negative 4 squared would be 16, which is greater than 9. So that satisfies the inequality. So with these quadratic inequalities, or really anything that's not just adding or subtracting or multiplying or dividing, you have to be a little bit careful about those inequalities, and maybe just thinking numerically about what kinds of numbers would make those inequalities true is your best bet there. Okay, so I have two intervals here as well. So I'm going to have another union of two intervals here. On these two intervals, though, I have the or equal to, so I'm going to use closed off brackets for that. When I write intervals, I tend to write them just like I'm visualizing on a number line, starting with the left end. So x less than or equal to negative 3, we would start at negative infinity, and we would go up to negative 3 and include negative 3. So I use a squared off bracket there. And then union, and then this interval here, which starts at 3 and goes all the way to positive infinity. All right, so there's domain of that last function. So when you learned about domain in algebra, you probably learned about domain in little pieces, thinking about different functions one at a time. Now that you're in calculus, though, you're going to kind of have all these different function types thrown at you all the time. So making sure that you have this little list handy in your head somewhere is helpful when you're thinking about domain of any function. We'll look at another video that specifically focuses on inverse trig functions. Each of those have their own separate domain restrictions that you have to be a little bit careful about for each of those.